All right, next up is Sajda, and he's coming from Colombia and going to talk about physiologically informed artificial intelligence.
So yeah, I want to say this has been really a pleasure to listen to all these talks. I have to say it's a little bit outside my field, but at the same point, I love being outside my field because I learned so much. And what I want to do is start maybe with a little story, a little anecdote, which explains kind of what my background is and how I got interested in this area. So about 6 years ago, I was invited by the Army Research Lab to take part in a workshop where they were talking about new programming, human machine, whatever you want to call it, human machine. And so my background is I'm a neuroengineer. I study the neuroscience of human decision making. I'm interested in decision making under fatigue, stress, high levels of arousal. I do a lot of machine learning. I don't really know what AI is, but machine learning usually applied to physiological signals. And I know nothing about the science of teaming, or at least at the time I didn't. So I was, on my way to the lab at ARL, and I'm trying to think, what am I going to say that's kind of intelligent within this context? And so I'm driving in my car, and I'm thinking about, all this semi-autonomous vehicles now, and there's going to be now autonomous vehicles. Elon Musk just said, by 2023, all cars will be autonomous. And I thought to myself, even if that jerk does that, I like to drive. I really do like to drive. And so I was thinking about a scenario that happened during this trip and how I would have liked to have teamed with autonomy, with a machine. And so the first day at this meeting, I was on time. I was actually early, so I'm driving into the parking lot, and the ARL folks were nice enough to have little VIP spots for those of us that were invited to talk. So I got there nice and early, and I was really happy. I got in, and I got my coffee. The next day, I'm running late, okay? I'm running late. I get in to the parking lot. There's absolutely, everything is taken. I'm going back and forth, and I'm really getting aggravated. And so what I thought of was, that's when I want my car to say, hey, Paul, don't worry, I got this. Go to the meeting, I'll park, right? And so that particular type of relationship that I was looking for between autonomy and myself really was one in which there was this just-in-time interaction where the autonomy delivered something I valued at a particular moment in time and when I was in a particular state. And so this actually has implications broadly in psychology and neuroscience. There's this kind of classic relationship between performance and arousal called the Yerkes-Dodson relationship. And we know that there's like this sweet spot of our level of arousal in which our performance on a task is kind of optimized. And so in thinking about this kind of scenario from the standpoint of more general human agent interaction, the idea is that, if I'm in a state where I'm kind of in my optimal state and something shifts my arousal level, maybe I'm late, maybe all of a sudden the task is very difficult, I'm distracted, I start to move down that curve, right? And what would be great with these just-in-time interactions, right, is for now autonomy to engage at that point. And that engagement now allows there to essentially be a performance envelope that I'll never go below, right? So that's one element. But another important element that's very important to realize, at least from the physiological point of view, is that there's actually then a chance with that intervention of autonomy for the autonomy to reduce my stress or arousal level so that I can recover. And so as a human within this loop, I realize that autonomy is playing a causal role in reducing my stress and fatigue. And there's a lot of evidence that that type of causal relationship, right, and how, let's say, a mother picks up a child and brushes them off after they've let's say, scrape their knee and takes care of them, that actually, we know, causes a cascade in physiological signaling that typically increases trust, right? So the notion of how we would actually intervene, these just-in-time interventions, as a function of physiological state, cannot just augment performance in the combined human-agent team, but also increase the human's trust in AI. So I put up this character here again. I've already mentioned him. So many of you know, obviously, he's working on self-driving cars and destroying Twitter and things like that. But how many of you know that he has a brain-computer interface company?
Neuralink. Neuralink.
Yeah, Neuralink, exactly. So Elon Musk thinks that the only way we're going to survive AI is by connecting our brain to it. I don't believe that.
And go to Mars.
And go to Mars, right? It's all about Mars. Mars is where all the potential new product lines are. And actually, his approach is like, really drill a hole in your head and put a chip in there. But all humor aside, the concept of trying to inform AI about our underlying physiological state, whether it's our brain state, whether it's our body physiology. So, there's a brain-body connection of which things like stress, fatigue, workload are all expressed across different physiological parameters. And what I want to talk to you today about is just how we might think about using physiology as a way to inform AI, not just as a new communication channel to augment human performance or kind of synergistically combine human and machine performance, but also potentially as a way in which to increase human trust in AI. So I just want to go through a couple of case studies, depending on how much time I have, which the first two will really look at the types of signals that we can measure reliably physiologically and how those signals can be used in solving specific problems of human-machine interaction under stress and fatigue. And those two will mainly focus on the signals, less of the integration with the AI. And then the last two, I'll talk a little bit about how these signals that we're decoding from the brain and the body actually inform AI in potentially advantageous ways. So the first example I want to talk about is one that's related to a phenomenon called pilot-induced oscillation. So I'm going to show this little video. You're going to see this is a French Saab jet. And this plane is landing, right, and obviously crashes. And you can see before the crash, there's this kind of oscillation. And the pilot was okay. He ejected. But it turns out this effect, this pilot-induced oscillation, you see not just on this jet, which is, probably a fourth-generation jet, for those of you that are jet aficionados, but even on newer fifth-generation jets. In fact, the 737 MAX was pulled off of the line because of oscillations that were related to how the signal from the avionics system was perceived by the pilots. Okay? So for a long time, the Air Force and folks in aviation thought, this is clearly just a problem where we don't have enough AI. We don't have enough automation in there. But it turns out this is called a pilot-induced oscillation, partly because it's the interaction of the pilot with the system, okay? And it's an interaction in a very kind of interesting way that is somewhat non-intuitive. Pilot is coming in and essentially there are two boundaries. There's the boundary, so the runway, and then there's potentially a stall angle, right? And the pilot is slowing down and trying to navigate between these two. The pilot can get into a state where, as they try to avoid one boundary, they react such that they actually overcompensate and move too fast to the other boundary. And what you know is that their arousal level shifts up, okay, and this becomes this positive feedback loop. And I'll explain that in a little bit more detail. So, the overall phenomenon is called boundary avoidance. It's part of we have this cognitive control system in our brain that helps us kind of take information from the world, decide how to act on it, generate a behavior, reassess the information. And so in cases where there are essentially two boundaries that are task critical. If I move past these things, I'm dead, right? Then we actually start to increase our arousal level, that our brain's cognitive control system moves into like a flight or fight response. So, I look in this direction, oh, there's a tiger here. I don't even look and spend enough time to say, all right, is that tiger, chained up or not? I just run in this direction, right? And so that's the same type of thing that we're seeing in this case of a plane landing. But it's not unique to that, right? So if I took, and I've actually done this example once live. So if you have a cup of water, right, and you're going, let's say I'm going over to watch TV in my house, right, and I have a hardwood floor, go across, no problem, don't spill the water, so forth. Now I switch that scenario. I put a brand new white rug my wife bought and a black cup of coffee. Your chance of spilling goes up like by several factors, and that has to do with the cost, right, of having that coffee spill, and you're balancing it between the two edges of the cup. So those are two examples of physical boundaries, but even abstract boundaries. When traders are trading between narrow buy-sell margins, you'll also see this phenomenon, this boundary avoidance phenomenon. And so, like I said, what they do is they overcompensate. They don't actually effectively integrate information from the environment to make a decision. They fall down that Yerkes-Dodson slope because of this positive feedback loop. So just real quickly, kind of what's happening in the brain, or what's the areas of the brain that we think are involved in this kind of funny interaction, right? Because it is based on a flight or fight response, which is important for us, right? But at the same time, it's detrimental in these cases. And in fact, getting back to why you can't just build a better airplane, the pilot will not let go of the stick. They think that they can get out of this oscillation, when in fact they can't, right? So there's this other loop in there that is effectively convincing them of something. They're basically, delusional, just like ChatGPT is sometimes. So there are three main areas. There's what's called the dorsolateral prefrontal cortex, very important for forming decisions. There's the anterior cingulate, which is kind of more in the middle of your brain, that kind of assesses error in your decision making, stores internal models of the world. And then there's this little nucleus in your brain stem called the locus ceruleus. And that actually is a major modulator of cognitive arousal and systemic arousal in your body. So, we want to kind of see, can we measure activity across this network in order to understand, is there a way we could assess this state of, or let's say the pilot, and provide some intervention. So we do this through, I think everything I showed today, we use virtual reality to conduct our experiments. And we measure across multiple dimensions of physiology. So everything from what your heart is doing, what your sympathetic nervous system is doing by looking at pupil dilation, parasympathetic to heart rate variability. And we actually did a study where first we looked at kind of open loop, how we would combine this information, these signatures, in order to make predictions about the underlying arousal state of the individual, of the pilot, as they're doing this task. And so the task they're doing is a simulated glide path task. So they basically are in a simulated airplane, they have a stick, and they're moving through these glide path rings, which some of you might have seen if you ever played a flight simulator. So after we did kind of an open loop studies, we said, all right, now we're going to close the loop and see if we can affect the actual underlying state of the individual as their arousal starts to shift. And so we used mostly in this case, the input measure was EEG. So we were looking at different spatial frequency relationships in EEG that relate to those areas that I talked about. And then we said, all right, we're not going to use AI in this scenario. What we're going to use is we're going to have feedback, neurofeedback. So the first thing we did, right, was we said, all right, what we'll do is we'll put a little bar, so in their heads-up display, that says, okay, this is, you're getting, your arousal is going up, or your neurophysiological marker of arousal is increasing. Anyone think that worked?
No.
No, exactly. It made it worse, right? They all started, they just crashed more. They stressed out. We said, all right, how about this? Let's take the signal that now we're measuring, and what we'll do is we'll modulate and change the gain of the control stick so that if they push a lot, right, they won't move quite as much, right? So this is like trying to change the gain and delays dynamically. Did that work?
No.
No. Why?
They push more.
Because
Yes, they push way more. So what, in fact, we had one Marine aviator, he broke my $3,000 joystick. So then we did a little bit more investigation into the underlying nerve science. And it turns out, so this locus coeruleus, this little nucleus, right, it turns out it's also important, right, for regulating heart rate. It's in fact, the firing rate of the neurons in the locus coeruleus is exactly tied to the heart rate. So we said what we're going to do is we're going to play a audio signal to the individual at a low heartbeat, just like 60 beats per minute. But the loudness of that is going to be controlled by this BCI signal, this signal we decode. And so we do that while recording all, and this is just a little example of the screen inside the goggles is really the view of the individual, but that's for the experimenter. And lo and behold, what we found was that when we feed back the information in that particular way, there was a dramatic increase in their improvement of performance, where that's defined as how long they could fly before they crashed, okay? And so we did this relative to two scenarios. One was silence, right, no feedback. But we also had to do something where we actually had feedback, but we had a sham. So what we did is we modeled the signal that was this BCI signal statistically, and then created a feedback that had the same statistical properties in terms of how often it moved up and down the volume of the audio signal, but it was not related to their brain activity. And none of the individuals could detect that sham case. Lo and behold, we were still significantly better than sham. Now, as a test to see what were we really doing, were we modulating arousal? We could look at two other physiological measures, which were not part of the prediction, to test to see if, in fact, we were affecting them at the end of the trial where the feedback occurred. And we found, for instance, that we saw an increase in heart rate variability, which indicates actually lower arousal, and a reduction in pupil diameter, indicating higher cognitive control. So the pupil actually is, I could talk about the pupil for hours. It's a very interesting and really super important physiological marker that obviously is easy to detect with things like cameras. But in addition to its dilation change as a function of luminance or accommodation, it's known to also have its dilation affected by arousal. So we saw this relationship between the physiological signatures and how we could use that information to improve performance in a way that we validated that in fact we were controlling the underlying cognitive state like we thought we were. Now this signal could be used to inform autonomy also of the state. But instead of jumping to how we might do that, now I'm going to talk about, okay, so that's a case of one individual, right, and decoding their state. Now let's consider team dynamics. So I'm also a big space buff. I love Nancy's talk. And so those of you that ever saw Apollo 13, you probably remember this sequence. I'm not sure the audio will go on, but in the movie Apollo 13, right, the astronauts have to work together, right, to create this burn, to realign them back to Earth.
It's all backwards, so
it's kind of like a team-based boundary avoidance task, because if they moved outside of this re-entry angle, they were going out forever. So just watch for a second and the communication they have between each other.
You up for this, Fredo?
I'm with you.
Or Fredo's got food poisoning for those that don't.
Standing by for corridor control burn.
Okay, Jim, you can fire when ready.
You are go for the manual burn.
6 plus 10 seconds. Mark.
Come on, baby. One more burn. 8, 7, 6, 5, 4. Let's just go.
So you can hear they're communicating, they're actually controlling different degrees of freedom of the spacecraft. So what we did is we wanted to understand this and within the context of these boundary avoidance type scenarios where clearly stress and arousal are modulated. So we created a version of this within virtual reality. We call it Apollo Distributed Control Task, and actually we're able to look at multiple dimensions of the problem, ranging from the type of communication the 3-person team had, to how things change as a function of difficulty in the task, to even looking at over weeks at a time as the team got more experience with one another, how the team dynamics changed. I'm only going to briefly touch on this. This is just the VR version of what you saw in the movie. The key thing is that each individual in the environment they control 1 degree of freedom. The degrees of freedom are all orthogonal, and they actually only have partial views of the environment. So they actually have to talk to one another to really control this together. And so the first thing we looked at, like I said, pupils on my, I love the pupil. We looked at pupil dynamics, right? And so we were recording.
A very good pupil.
Yeah, very good pupil. We, in addition to looking at the pupil dilation, we looked at eye movements. We were recording EEG. We were recording all of the communication. The first thing that we found that we thought was really interesting was, and if you really focus on the top row, where at 0, that is when they pass through a ring. Okay, so a ring is at, you could think of at time 0. And each one of these columns is a different position, right? So there's a yaw, somebody that controls the yaw, somebody that controls the pitch, and somebody the thrust. And what you're seeing here are essentially the pupil dilation leading up to the ring and then as it passes the ring. And the first thing you notice that as the changing colors represent the changing difficulty level. So red is the easiest, blue next, purple the next. And so one thing you can see is there's definitely separation, right? The pupil, when the task is kind of easy and I'm gonna I make it through the ring, the pupil dilates, meaning my arousal increases, and then before I pass, it starts to recover, it constricts, so my arousal level goes back down. And that as the course is more difficult, that essentially dynamic going from increasing arousal to decreasing arousal gets bigger. Now also super interesting was the fact that if you look at where this peak is, right, so this is the yaw and the pitch. For the thrust position, there's actually a shift in time, right, backward. Whereas the task is really easy and I pass this ring, there's the recovery happens sooner. And that's actually because the thrust player has a little bit better field of view and knows when they're going to make it through, right? So from the underlying physiology, we were able to infer which player had better situational awareness of what was going to happen as they went through the course.
Did they all succeed or some fail on these curves?
No, so this is all where they succeed. The bottom is where they fail.
Okay.
Yeah, and actually the interesting thing when they fail is there's actually very little difference in the slope, right? So if they're going to fail, whether it's easy or hard, their arousal level just goes up, right? So now we also wanted to look a little bit about the interaction between these teams and what it means to be in sync. Okay, so there's a lot of work has been done in teaming, looking at synchronization between team members across different inputs. We had a hypothesis that in a high-performing team members' actions are predictable by the behavior and physiological state of another team member. So what we wanted to do is take our physiological data and use it to predict action, a future action of another team member. And the way we did this actually was using, those of you that know this is a transformer model. This is what ChatGPT is all based on, these types of models. And so we treated this a lot like a problem, like a translation problem, where we said, all right, we could take two of the players, the yaw and the pitch player, and input into this model the pupil dynamics, their controller input, their EEG activity. And what we want to come out of the model is the thrust control input like a second or two later, right? And the hypothesis was if these physiological signals were in fact informative of the interaction across team members, then as we add inputs, we should see better and better prediction performance. And lo and behold, that's what we saw. And so just to interpret this graph, the idea here is that for this color here, we take just the action. So just essentially what the joystick input was for the yaw player, the joystick player for the pitch, and then at a second later, compute the joystick for the thrust, right? And we now, as a metric, we look, all right, how correlated is that prediction with what actually happened? And so if you just use the action of the two other teammates, you get, something like 0.075 correlation. Now if you add the pupil into the mix, so you put both the actions as well as the pupil dynamics of these two individuals, you start to get an increase in that correlation between what you predict and what happened. And lo and behold, EEG more, and then if you add all of these together, you start to get correlations that are reasonable. And these are continuous inputs, right, that are being predicted. So far, all I've done is like kind of shown you some of the physiology, how you can decode it, how that signal, could be used in a human agent team, but I haven't actually put it as an input into the agent side. So here's these last two examples I want to talk about have to do with this scenario, which I'm sure everybody has had before, is that we walk down the street, right? And we're implicitly labeling our world, right? We're walking around, we have these fleeting thoughts of things we see. Maybe there's, some restaurant, and you look down, it's like, yeah, I'm kind of hungry right now, or, happy hour, oh, that wouldn't be bad. Or maybe you have some object goes by a car, and you wonder, what model is it, or I wonder how much that costs. This next one I think would be super useful, particularly to myself, is I'm not very good in remembering names. I love wine though. Is that you see somebody on the street come by and you orient to them. So when I say orient, you attentionally shift you shift your attention to that person, and you don't maybe not know the person's name, but there is a strong response in your brain that has to do not with the physical orientation, but the attention-oriented response. And so this kind of response, so first of all, anyone that's read the popular papers, there's all this stuff about, these kinds of thoughts, AI is going to read out of our brain. There was a paper that just came out in Nature Neuroscience. In my humble opinion, it's all garbage. Because, I know I say that pretty strongly, but there's a lot of the details. We're nowhere near even knowing what a thought is, quite honestly, or how it's represented. But there are some kind of macroscopic signals, like the orienting response, the fact that if a gunshot just went off, right, all of a sudden there would be a response in my brain that's pretty broad and can be measured non-invasively with EEG that would that I could measure, and my pupil would dilate, right? And so you could imagine scenarios. I'm looking for, I'm hungry for an apple. I see a banana, no big deal. I see an apple, oh yeah, I want to eat that. I can measure, not that I wanted an apple, but that I oriented to something I just saw in the environment. And so this gets into how we might think about using this orienting response to actually couple to a piece of AI or machine learning. And so one thing that we did is we said, all right, let's say we'll go back to our, autonomous vehicles again, for lack of any other better scenario, and we'll imagine being in an environment where this autonomous vehicle has to figure out how it should brake, right? So it turns out the way you drive is not like the same way you want to be driven. So as soon as if you drive your car, you take all those parameters and throw them into your semi-autonomous or autonomous braking model, you're going to hate it, right? So there's this notion of using information from the state of the individual to tune or train the AI in terms of learning how to brake. And that could be not just like how far away you are from the car in front of you, but also there might be certain things you're interested in. Like you're out in the woods, woods, maybe out somewhere taking in the scenery, and so you're interested in certain types of scenery, you orient to that. What can happen is the car can detect that you oriented, and then from its external sensors, find out what's in the environment, use that as training data to now build models of other things in the environment similar, right? And then adapt its braking policy. So we did this, I'm not going to get into the details, but the idea is you can use in a reinforcement learning model, much like DeepMind and Google use for AlphaGo, you can use rewards that include traditional rewards or models like being safe and keeping a safe distance from the vehicle in front of you, but also user preferences that are inferred by the physiology. And you can combine those together to really optimize the experience for the individual. I'll just jump over these results. You can also tie this in to this notion of thinking. You can start to really play games in how you could use this, right? So one we've been playing around with is superhuman perception, basically having eyes on the back of your head. And so the idea would be that you're in an environment, and once again, this is all we have done in a VR environment, where an individual is kind of looking for objects that they're interested in, right? So, and we can't, they could change on the fly. They could be interested in a banana, and then the next time a cell phone. And so we use the signal that we're now decoding and detecting from all this physiology to label moments in time in the world that then are used as training data into a machine learning model that then has sensors pointing in all different directions and can actually point out to me while I'm, let's say, searching an environment where other things might be in the world. That's what these little red arrows indicate. So in this kind of environment, you've got the AI is using this orienting response to now cue you that other things that grabbed your attention are behind you. So I'm out of time, so I'll just go through a couple of take-home messages because there's a lot here. So the first is that I really think physiological data, both from the brain and the body, really can be used to infer what we could consider covert state. So state that's not easily inferred from behavior, and this could potentially enhance information delivery and interaction between the human and the AI team. Caveat here is, though, this kind of data is very noisy, right? So, even, like I said, pupil size is confounded by light changes, accommodation. And so I think the most successful approaches will use kind of a multimodal, multifaceted approach, and also modeling to understand how our physiology changes in different contexts. And then lastly, and getting back to, even though I didn't say anything about this directly in the work that we've done, I do believe this just-in-time intervention is kind of key in the fact that we assess the value of something typically at a moment that's related to our underlying emotional and arousal state. And so the more that AI or agents can kind of be tuned to our state, the more likely is that we'll trust them, or at least trust them with our lives. So with that, I'll just have acknowledgments to all the students that did all the work, and ready for questions. Yeah.
So I really like your presentation. When you're studying arousal, like a team study in the lab, can you really, the problem that we have studying trust in robots or trust in AI is that trust isn't as relevant when you're not stressed out and where there's no risk. And so can you put people under that much risk in the lab?
Yeah, no, good question. I mean, I think that one thing that, so there's obviously a spectrum, right, to arousal and stress. And so using VR is actually extremely important for really driving arousal and stress. I don't know if you've ever done this building game, Jumper, I think it's called, where you feel like you're at the edge of a building, right? My heart rate got up to like
I
one.
can't jump.
Yeah,
It's really
frozen,
really
right,
difficult
frozen, right?
to jump off the building.
Right. And even though you know it's only 6 inches, right?
Yeah.
Right, it's extreme. So we can get that far in the lab. You know, the IRB after that will but no, it's important. I do think,
The glass floor in high buildings.
glass. Yeah, glass, but I've never had it as bad as I literally was frozen. And somebody held my hand, so I could disconnect from the VR, but it took a moment before I actually convinced, and I think I went kind of step down as opposed to jump. But I think, this gets to the fact of how does this ultimately translate? And it is true that, part of what we're trying to do is work directly with Army research labs, Air Force research labs, and then they have better ways to do a lot of this. So, yeah.
So how would this translate into an actually Army situation, right? Are they thinking about helping soldiers in specific situations or pilots or something by overriding the oscillation response, for example, or
in the case of the plane. Yeah, no. So part of that. So I think part of what they're looking at to see is if you can train individuals to get themselves out of that over time. So everything that we did, right, this neurofeedback, we never tested whether there was a neuroplastic effect, whether after you take them out of the feedback, that ability to adapt is stuck, right? But I think, so that's, and interestingly enough, so I did this first with DARPA and then the Army. Javi's here to help fund some of this. In the Army, right, you don't think of them having planes, but they have the same problem. Somebody told me with some of their vehicles. There's something called a Stryker vehicle. And so how it gets used, I think, is still up for debate. Where does it fit in? I do know that when they're thinking of teams, particularly these hybrid teams that are robots and warfighters together, one of the challenges is how does the robot start to know the states, the physiological state of the human warfighters? Because these guys end up really knowing, they can look at each other and assess whether or not somebody's stressed out, they need help. So it's another communication channel. Yeah.
Great presentation. With my team at Purdue in aeronautical engineering, we worked on that topic of cognitive engineering, enabled autonomy or control. And there, the focus was very much of the tactical thing, predicting whether can actually someone fly, and that works quite well. Now, the goal is to move up to more higher level decision making, which is, even decision on planning where to go, and there's this concept, situational awareness. So, as a neurologist, my question is, could we use, I know there's a lot of work on that eye tracking data, and that's useful, predicting situational awareness at the attention level, but can you actually go to that reasoning understanding level directly from the signal to enable actually a control with, real-time feedback, as you mentioned?
No, really, fantastic question. I don't know. I think right now we don't know how to decode that high-level reasoning, but I think what we could do, right, is we can contextualize that reasoning based on the physiology, right? So if I'm in an environment and my arousal is shifting, maybe I'm now discounting, particularly if I'm in a team, I'm discounting individuals who are in a high arousal mode because their decisions are likely to move down on this. So there might be a way it could be used to arbitrate. But I think the other thing is, so I'll tell you, there are, particularly with EEG. EEG is a really noisy signal, but some work that I've been doing with a company is if you can collect enough of this signal over a long period of time in naturalistic environments, you start to be able to see kind of these patterns of brain dynamics that you can't really get in the lab because it's not real. It's not And then as soon as you can detect these different patterns or these states, then you can track them, right?
Because we've just started to collect data. I'm not presenting anything on it, but we have been starting to collect data on that, and now this next goal and discussion with our neuroscientist group on how to encode it correctly. So I'd love to, maybe continue.
Thanks, Chris. So a lot of this hinges on the accuracy of the data. I'm in multiple communities, and in the IS community, this stuff seems to work well. Physiological, neurological, like it seems to be error-free almost, right? And then in the engineering world, when I do research there, they complain about it's full of noise. There's a lot of noise. And so why is there so much of a disagreement on how useful this data is? And you mentioned yourself that there was an article that you seem to disagree with it recently. Why is there how come there's so much disagreement on what was supposed to be object data that I've been told helps to replace my error-prone perceptual data?
Anybody a neuroscientist? Oh, yes, right. I'll tell you this. So it's the difference between engineering and neuroscience, right? So, and maybe it's biology too, but neuroscience, part of it is there is this compelling, we want to understand thought, right, all of this, right? And so there's always a story about what we see, and then you build a story about it. Like, is this where emotion resides, consciousness? But neuroscience tests at P of 0.05. Engineers test at what? Like 6 sigma, right? So there's this whole difference in terms of an effect, whether that effect really has any, practical value. So this Hobby will also say the data is really noisy. You can start getting some insight, but then we always get to exactly what I think Nancy was saying is, you got to push it. You got to say, all right, now we've done it in a lab with this. Now, put it on a real plane and see what happens. I'll tell you one example. So they did try to do this with we were partnering with the Johns Hopkins Applied Physics Lab. Mm-hmm. So their job was to take an EEG cap and put it on CalSpan, I think is it. Basically one of these planes that the Air Force has, and they did these PIOs in the air. The biggest problem? Vomit all over. Sorry. But anyway, these things are not meant to, because there's all these other factors, right, that happen, and the motion and all of that. So there's still engineering challenges there, but the thing is there is a signal, and how it translates is important. Yeah.
Are you able to parse out, how can you tell if it's just correlated reactions, individual reactions to a shared external stimuli versus synchronization across individuals?
Oh, good, very good question. So right now, we are trying to, in addition, look at causal modeling, where we're factoring out certain confounds, and designing a new experiment where we have additional perturbations that we're going to try to use to make sure it's just not an external, external.
Like in the rock band, the bass and the drums are very synchronized,
No, I totally agree. That's always one of these issues where. So I guess the thing is, what they see is all different. So there are these. It's not totally different, right? But they're seeing a different part of the environment, and they're controlling slightly, as opposed to some of these studies where essentially everybody watches the same exact movie or same stimulus. What we call ISC, synchronization between individuals. But no, it's still a great point. And maybe
let's do the last question.
Sorry.
Yeah.
A number of your examples seem to look at what I want to call it, sort of calibration, between agents. So your first one, the calibration between the pilot and the AI system, or the system and the flight, right? And then your example from Apollo 13, right, and your simulation, trying to figure out what's the optimal way to get these different agents to calibrate together. And I'm curious, at what point do you say it's really hard to get these agents to have any kind of calibration that's really robust, and we should just automate the entire thing? Is there is there a point at which that happens? Because presumably an autopilot for the landing wouldn't have the same kinds of calibration issues of the pilot with the control system. nor would the three different fields of vision and partial ability to see what's going on. So how do you think about where do we put human agent collaboration in play, and where do we just remove the humans and have just the automated agents do it?
Fantastic. And I think even the Army asked this question,
Yeah.
or to themselves, in fact. So I don't know. I mean, I think if we really, it's 2023, we don't have our self-driving cars, right? And so I think a lot of these problems that we think, automation will just solve, there are these edge cases which are the real problem. It's hard to predict, right? So it's definitely possible that someday all this stuff gets automated. But what I would kind of argue is that so it might be that these types of signals related to physiology and brain state are not useful in this particular scenario, but they can maybe inform other things, like what was said before by Sabine, where maybe that can also be used to adjudicate high-level decisions.
Yeah.
But you're absolutely right. Like, I think I was at a review 4 or 5 years ago, and some general or somebody said, "Yeah, well, why don't you just replace it with AI?" Well, it turned out when I talked to the pilots who fly the F-35, right? Because when I talked to Lockheed Martin, they said, "Oh no, we never PIO." You talk to their pilots, "Oh yeah, it happens all the time." So,
Well, the classic conundrum in automation, right, is that you automate all the low-level tasks and skills, and then you're left with the edge cases where you need an extra dose of skill to be able to solve the problem.
and it's so hard to hand off the edge case, right? Because the person is not ready for the edge case.
And then if the machine just breaks down, your Apollo 13 example is great because if I remember correctly, the computer shuts down.
Yes, exactly.
Right?
That's
And
the
they
whole
can't,
problem.
and
They
so
have
the
to.
computer can't do this, and so now these guys have to coordinate manually to make it happen. And so you end up in these situations where you're training for the 0.01% chance that this is going to occur, but how do you do that effectively?
Exactly. Okay, thanks very much.